Welcome, guys. This is the APES Chapter 11 lecture. You see on the screen we're looking at geology and non-renewable mineral resources. We tend to think about non-renewable resources as in petroleum and oil and fossil fuels. But we're going to expand that a little bit to look at things like rare earth metals, things like copper, things like coltan, things along those lines. There are 17 rare earth metals that we used to manufacture things like our cell phones and our new TVs and things like that. So there are a lot of costs associated with using those rare earth metals. I'm going to have you guys look at coltan specifically, but like many of the natural resources we've looked at, they aren't equally distributed. They tend to be found in poor developing countries. And so the true cost, those externalities that we've talked about, fall on other people as opposed to being harvested here in the U.S. and harvested in ways that follow our laws and regulations and things like that. So how do geological processes relate to society and the environment? Kind of what I talked about. They're produced by, so our mineral resources are produced by these geological processes. Think about creating diamonds. It takes millions of years to take something organic and crush it down to a diamond. And so that makes it a non-renewable resource. Our cutoff for renewable versus non-renewable tends to be 100 years. So if something can regrow in 100 years, it's considered renewable. That's why something like wood would count as a renewable resource, because we can regrow a tree in less than 100 years, unless that's some kind of crazy, slow-growing tree. So when the Earth cooled, we're going way back in time now, we had three zones that were created. The core is kind of the middle. There's the inner core that's the hot, solid sphere, so it's essentially rock. And then there's the outer core, which is molten liquid rock. You may have heard of the asthenosphere, that the plates move on and all that kind of stuff. So we'll get more into that here in just a minute. Mantle is the semi-solid liquid with the ability to flow over geologic time, kind of like magma. And then the crust is the thin outermost layer that we interact with mostly. Okay, so something that is really important in terms of volcanoes and earthquakes and things like that are these convection cells. So the uppermost mantle is solid. So it's a solid floating on a liquid, essentially. That's where that asthenosphere term comes from. That's what kind of carries the plates. The high heat in the core and the inner mantle are going to generate convection cells that are going to move the heat and the rocks around. I got a picture on the next slide that will show this. Let's just go right to it. Okay, so we've got this heat that's happening in the Earth's core. Hot surfaces, hot substances rise. So as these things get hotter, as the liquid melts, it's going to cause the liquid magma to move towards the surface. Gravity is going to be at play here too, because you're taking a liquid and you're spinning it in circles. So we're going to get this kind of movement where it heats up, reaches near the surface, cools down, returns back to the core. So that's what we're talking about when we say a convection cell. We've got the same thing happening here. Notice what's happening. I know you can't really, it's tough because the picture is so small. Right here we've got a diverging boundary. So we've got magma going right, we've got magma going left. Well, this magma going right is going to carry the plate that sits on it to the right. The magma going left is going to carry its plate to the left. Now we've got an opening where some of this magma can breach the surface. I've talked a little bit about the plates. Over geologic time, these plates have moved, split apart, and rejoined. There are something like 6 or 7 supercontinents that have been theorized. You guys have probably heard of Pangaea. That's the most recent supercontinent. But this is all really attributed to tectonic plates and their movement. So if you look here, you see the plates. The red lines are the plates. So lots of little kids, when they learn this, they learn, oh, look how Africa and South America fit together. And look how if you roll this way, it fits together. And if you roll this land formation back here, it fits. Yes, absolutely, that's valid, and that shows how Pangaea might have fit together. But it's not like this space right here is just water all the way through the earth. There's rock down there too. So when we talk about the amount of rock down here, think about what would have had to happen for, let's say right here, for the Horn of South America to fit into, I guess for this part of South America to fit into the Horn of Africa. There's all this rock that's just going to have to have been created. Well, this is a divergent boundary, so we're adding magma to this to these plates at about an inch a year. So what are Earth's major geological hazards? You know a lot about most of these. Anyway, I'm just going to try to fill in the gaps. Volcanoes are essentially places where plumes of magma are going to reach the surface. Often they're going to be around tectonic plate boundaries. Eruptions are going to push lava, they're going to push ash, they're going to push tons of gases, tons of methanes and phosphates and things like that out into the environment. A lot of it directly into the atmosphere because we've got an eruption happening. And then we get lots of new fertile soil created by the erosion of volcanic rocks. So they do have lots of nitrates and phosphates locked up inside of what becomes a lava rock. So we're often going to see drastic destruction as these volcanoes erupt, but then we get lush secondary succession happening. So that's really not uncommon as well. The other natural disaster or geological hazard that we're going to focus on are earthquakes, and that's mostly because those are related to the tectonic plates as well. So and when we talk about earthquakes, think about the building up of tension and then the sudden release of pressure. So we'll talk about the different types of boundaries, but think about a boundary where the two plates slide past one another. You've got one going north to south, one going south to north, and they're pushing against each other really hard, and then suddenly they slip, and then we get what's called an earthquake. So we'll talk more about that in the debrief in person. The other three that we didn't really get to, tsunamis, those are often caused by earthquakes. That's what we're seeing here most recently in Earth's history anyway. We see an earthquake in the ocean, and that causes a major wave that then causes all sorts of destruction. Erosion and landslides play into one another. So a lot of rainfall is going to lead to erosion, and then landslides, of course, are going to be kind of extreme events based around the erosion. So what are our mineral resources, and how long might those last? So remember, we are talking about mining here, but we're trying to focus not specifically on fossil fuels. We're trying to expand our definition to include things like copper and other precious metals. So, So what are minerals? Naturally occurring chemical elements with inorganic compounds. Or inorganic compounds with regularly arranged atoms or ions. Okay, so think back to the rocks and minerals lab. Rocks and minerals are not the same thing. They're similar, but different. So a mineral is going to have a regular structure. It might be something like salt that has a structure. Some contain only one element. Some are like compounds, like quartz is a compound. But typically we're looking at something like one element, like gold, salt, things like that. Some kinds of salts. So what are rocks? They're sort of similar, except they're not going to have regularly arranged atoms or ions. So they're going to kind of be stuck together, crammed together somehow, some way. So we got three different types of rock. Hopefully you know this. Sedimentary rocks are those formed from sediment. So things like sandstones and shale. Igneous rocks are going to be things that are formed from magma and lava, things like granite. And then metamorphic rocks are going to be things that are one of these other two that are then changed in the earth. Metamorphosis means change, so things like slate or marble have been changed, usually by some sort of high pressure and some sort of high temperature causes those rocks to change somehow. So the rock cycle, you'll hear a little bit about the rock cycle as we move through this. It's the process of making rocks. It's going to also include things like erosion and melting that we see there. So we have a rock, then we wear on it with water for a long time, and that sediment creates a different rock. Then that rock gets buried and gets pulled into the earth. Kind of talking through this picture. So that rock gets buried and pulled into the earth, gets heated, gets turned into a metamorphic rock that then is used for something else, and maybe it weathers. And like all of our elements, it's a cycle. What's here is here. Ore here is a key term that came up in our mining intro lab. Ore is going to be a rock that contains valuable minerals that can be mined or processed effectively. So that's kind of like the raw material. That's what comes out. We do have about 60 of the metals in the periodic table. The whole middle of the periodic table are metals, and we do mine about 60. And then, of course, there are non-metallic minerals and other things like that we pull out, like sand and gravel and limestone, of course, that we use. So those would all be considered non-renewable. Remember, the cutoff is whether it regenerates itself within 100 years. So something that I asked you, I think it was on the Cookie Lab, talked about the fact that in the 60s, I'm forgetting the details, but a long time ago, the copper that we pulled out was like 80% pure. And now the copper that we're pulling out of the earth is like 5% pure. So we've got a lot of impurities and less quality copper. Well, that should make sense. Like, you're going to get the easy stuff first. So what you're going to pull out is going to be big chunks of copper. And then once you run out of these big chunks of copper, you have to start searching. And you're looking for smaller and smaller amounts and less pure examples, things like that. So I think that's a pretty common sense idea. You just got to kind of logic your way through it. So a reserve is going to be basically like a big pool, like how much of it is available. We expand those reserves when new sites are found, when we can find more, when prices increase, so demand goes down, or when extraction becomes profitable. So we're going to expand our reserves. You hear about reserves of oil every once in a while with respect to politics. We have backups, reserves of oil. Well, when we find new amounts of oil, we can save more. When the prices increase and people aren't buying as much, we can save more. When something becomes suddenly profitable, we can add more. So these things are really economic ideas. Depletion time is the time to use 80% of the resources at a given rate of use. Here's kind of a graph that shows that. What we're talking about here is how do we know how much to build up as our backstock, as our backup amount. So of course, supply and demand affect one another. If you haven't taken econ, you'll come to know and love this really well. But anytime the supply is scarce, the price rises. That makes sense. If there's only a few of something, people pay more to get it. Factors that limit mining lower grade ores. So lower grade ore means more impurities. Sorry about that. There's more rock to process. It just takes more work. It takes more water. It takes more of everything to get at those the lower grade ores. In terms of biomining, we can use bacteria to remove ore from the rocks, but it's going to take a really long time because that bacteria is going to take forever to quote unquote eat whatever those minerals are. I'm sorry, the rock around the minerals. So we can mine in the oceans. If you've seen the Deepwater Horizon movie or you remember that explosion, we know that mining happens in the ocean. Notice that most minerals are in such low concentrations it's just not profitable to mine them. It's really expensive to mine in the ocean. So sometimes along the coast and along the continental shelves that are just off of the coast, we can mine some things because it's not as expensive. You don't have to go 100 feet down to reach the bottom. You go 20 feet down to reach the bottom, or 10 feet down. We also can mine minerals near volcanic regions on the ocean floor, in those hydrothermal vents that you hear about sometimes. And we do deep sea mine sometimes because our minerals become more and more valuable. You see China is using some remote controlled things like submarines to explore hydrothermal vents. But yeah, so it's possible, just not real practical at this point. So I will finish 11.3 with video 2.